Hello everyone. Under the classifications of discrete time signals, we have already covered deterministic and non-deterministic signals. We have also discussed about the differences between causal, non-causal and anti-causal signal. We have also discussed about symmetric and antisymmetric signals with some examples. Now here in this particular session, we will discuss everything about energy and power signals. After that, we will cover periodic and aperiodic signal. So let's start. So basically, a discrete time signal is said to be energy signal if its energy E is finite. That means we can say that E has a value between 0 to infinity. It should always be between 0 to infinity, but should not be equal to 0 or should not be equal to infinity. Now in the same way, a discrete time signal is said to be a power signal if its average power P is a finite number, or you can say P lies between 0 to infinity but should not be equal to 0 or should not be equal to infinity. Now for an energy signal, the average power is always equal to 0, and at the same time for a power signal, the energy is always equal to infinite. So this is the reason energy signal and power signal are always called as mutually exclusive. Now if a discrete time signal x of n is given, then how do we calculate the energy and how do we calculate the average power? So basically, the energy of a discrete time signal x of n can be calculated as capital E is equal to summation n equal to minus infinite to infinite absolute value of x of n square, and the average power P is equal to limit capital N tends to infinity 1 upon 2n plus 1 summation n equal to minus n to capital N absolute value of x of n square. So this is how we can calculate the energy and power of a given discrete time signal. Now there are some signals which do not follow either the condition of energy as well as the power, and such signals are called as neither energy nor power. Now the energy of a periodic signal x of n over a single period, say over the interval n lies between 0 to capital N minus 1, is finite if x of n takes on finite values over the period. So this is a very important point, that over a single period between 0 to capital N minus 1, if it takes a finite values, then it is always a energy signal. And the energy of a periodic signal for n lies between minus infinite to infinite is always infinite. These 2 points we need to remember about the energy signals, and these 2 points are very important from the gate examination point of view. Now what about power? The average power of a periodic signal x of n is finite and it is equal to the average power over a single period. Now if x of n is periodic signal with fundamental period capital N and takes on finite values, then its power is given by capital P is equal to 1 upon n summation n equal to 0 to capital N minus 1 mod of n square. So this is the formula of power for a periodic signal. So you can see that n equal to 0 to capital N minus 1 has an n number of values. So here I have written 1 upon capital N. In the same way, previously in the original formula of power, we have seen that 1 upon 2n plus 1, because n is equal to minus n to capital N has total number of 2n plus 1 values. That is why we have taken 1 upon 2n plus 1. Now here in this particular slide, I have listed out few of the examples of energy signals, some examples of power signal, and I have also included few of the examples of neither energy nor power. We will take each and every discrete time signals given over here and we will calculate the value of energy as well as power, and we will check whether the given discrete time signal is energy signal or power signal. So basically under the energy signal we have two examples, x of n equal to 1 upon 2 to the power n u of n and x of n is equal to del of n. So x of n is equal to del of n is a unit impulse function, and we should keep in mind is that the impulse function is always an energy signal. Now x of n equal to 1 upon 2 to the power n u of n, you can say in any exponential, if this particular factor is less than 1, then I can say that the signal will always be an energy signal. So we need to remember this one also. Now coming to the examples of power signal, the first example is e to the power j pi n by 2. So this particular signal is an example of complex exponential signal, and we should always remember that the complex exponential signals are always a power signal. Now the second example is x of n equal to sine pi n by 4. So basically this sinusoidal function lies between minus infinite to infinite, and between minus infinite to infinite the energy will always be equal to infinite, but the average power has some finite value. So that is why this particular signal is a power signal. Now in the same way, x of n equal to cos pi n by 4 or any cos angle is always a power signal. Now next is x of n equal to u of n, which is a unit step signal, is always a power signal. X of n is equal to k, where k is constant, is also a power signal. Now we discussed already that all periodic signals are power signal. Now here are some examples for neither energy nor power. As you can see, this is an exponential function, x of n equal to e to the power 2n u of n, x of n equal to 2 to the power n u of n. So you can see the factor 2 in this particular exponential is greater than 1. So I can say if this factor in an exponential is greater than 1, then such type of discrete time signal is always neither energy nor power. Now you can see here is that e is always greater than 1. This particular exponential is also neither energy nor power. Now next example is x of n equal to r of n, that is unit ramp signal. So unit ramp signal is always neither energy nor power. Thank you.